All right, this video is for AP Calculus BC. We're going to talk about another integration technique. This one's called partial fractions or partial fraction expansion. This one is used frequently. It's found pretty much every year, I think, on the AP Calculus BC exam, and also we use it a lot in Calculus 3. So I would say this is probably the third most popular technique after U substitution and integration by parts. Okay, let's take a look. So partial fraction expansion takes advantage of a procedure that we learned back in Honors Algebra 2. Well, actually, I think it used to be included in a class like Honors Algebra 2, but it has been taken out and put back in at various times. So you may not have seen this, but basically the idea is that if you have a fraction where or a rational function where you can factor the denominator. So let's say that you have something like maybe some number like 2x plus 7. And on the bottom, we have a polynomial that can be factored into x minus 1 times x plus 2. Then there's an algebra procedure where you can say that that is equal to some unknown constant over the factor x minus 1, and then plus a different unknown coefficient over x plus 2. And there's a procedure we can follow to figure out what this a and b constant are. Okay, there's a bunch of details here. If a couple of things before we get to this, but mostly we're handling cases like this: two linear factors, and where we start out already where the degree at the top of the numerator is, say, degree 1, and the degree on the bottom of the numerator is degree 2. So a lot of this has to do with additional things that can occur but don't frequently occur. I'm going to read through them quickly, but then we aren't going to really see much in terms of examples of that because these pair of linear factors is the most common situation. Okay, first of all, if you did have a degree in the numerator that was not lower than the denominator, so if you had something like x cubed plus x over x squared minus or plus 4x minus 4, right, you would first do polynomial division to divide that, and you would get some number and then plus a remainder, right? And you can do the partial fraction expansion on this part. So you would first divide if you happen to have a higher denominator in the rational function, the numerator. What you need to do is factor the denominator into factors, and those factors can be of the form constant x plus a constant to any power or a quadratic. Right? For every linear factor, for example, x minus 2, 2x plus 3, or maybe you have 2x minus 3 times x plus 2 or something like that, you're going to put a separate factor for each one with a constant on the top. If you happen to have something like this, let's say we had 2x over x plus 2 squared, so if that was repeated, then you would first put a constant over that with just x plus 2 without the square, then you would have a separate one for the x plus 2 that's squared. Okay. If you have quadratic factors, so if you have something where the factor itself is quadratic, like x squared plus 2x plus 3 or something like that, and then that has to be replaced with, maybe we have that factor along with another factor, x plus 2. Maybe there's 3x plus 1 or something on the top. This linear factor would get its own constant over x plus 2. But to handle a quadratic factor, you have to put 1 degree lower. So if this is x squared plus 2x plus 3, you have to put bx plus c. So basically on the top of the fraction for that factor, you have 1 degree lower polynomial with constants for all of the multipliers of the variables. So in the case of a linear factor, this is simply a constant. In the case of a second degree polynomial, you would use a first degree polynomial, a line, and have a separate constant for the slope and the y-intercept there of that line. Right? And then what you're going to do is get a common denominator, regardless of how you set this up, so that everything is over the same denominator. And then you will set the numerators equal to each other because you can no longer consider the denominators. And then we will gather like terms and match the number of like terms on each side of the equal sign to come up with multiple equations to form a system that we can solve for the remaining unknown coefficients. Now that sounds very complicated to explain, and these rules are complex, but in reality, the case that we see the most, it's fairly easy once you see how it works, but this is the full procedure laid out if you want to see it. Okay, let's take an example. Now this x squared plus 6x minus 7 we can factor because that factors into x, let's see, x plus 7 minus 1, is that right? X plus 7, yeah, x minus 1. So we'll check that. X squared plus 7 minus 1 is plus 6x minus 7, perfect. So what we're going to do is we're going to take this integrand. Usually we will do this on the side, with side work. We have x squared. I'm going to use the factor of 1 here. So the numerator of the integrand here is 3x minus 5. The denominator can be factored into x plus 7, x minus 1. So what we're going to do is we're going to postulate that that is equal to some unknown constant over the x plus 7 factor and plus some other unknown constant over the x minus 1 factor. All right, it doesn't matter which order. And then we're going to do whatever we need to do to get a common denominator. So if this is x plus 7, to get this common denominator, we have to multiply this by the other one's denominator, x minus 1. And we have to multiply this term by the other term's denominator, x plus 7. Right, so now at this point, we have the same denominator everywhere. So for the left side to be equal to the right side, the numerators all have to be the same. So usually I will write this again. I'm going to move this to the right-hand side. So this is a times x minus 1 plus b times x plus 7 must equal 3x minus 5. And we don't have to worry about the denominators anymore because now they're all equal. And then we will go ahead and distribute to get rid of all parentheses. So this is ax minus a plus bx plus 7b equals 3x minus 5. And the goal is to figure out these two constants. What is a and b? So to solve for two things, I have to have two equations, but right now I only have one equation. So this is the clever bit. What we can do is gather up the like terms. These terms are both x terms. So I can say there's a total of a plus b x's on the left side. And then I can lump all the constants together into a term, negative a plus 7b. Now on the right hand, I have 3 x's, and I have a constant, which is negative 5. Right? So I've gathered up the x terms on both sides and the constants on both sides. So what we're going to do now is we're going to make a little system. We're going to say the number of x's over here has to equal the number of x's over there. A plus b has to be 3. And the constant over here has to match the constant over here. Negative a plus 7b equals negative 5. Now, that was a way to cleverly get two equations out of this one equation. And we need two equations because we need to solve for two unknowns. Now, you can solve this system in any way. On this first one, I'm going to show you all three most common ways. The first way, what I would probably do here is just the algebra 1 idea of elimination. So let's look at that way to solve. So we're going to solve this system. One way to do that would be just to say we've got a plus b equals 3. We have negative a plus 7b equals negative 5. So if I just add these equations together, the a's are eliminated. We get a total of 8 a's equals, let's see, that would be negative 5 plus 3 is negative 2, right? And that means that I've got b is equal to negative 2 over 8, or negative 1/4. And then you can back substitute, because if a plus 3 has to equal 3, and now I know that b is negative 1/4, I can plug that in. And then to solve this, let's get rid of the fractions. So I'm just going to multiply everything by 4. So that's 4a minus 1 equals 12. Right? So that's 4a equals 13. And so a would be 13/5. Right? So we can solve that way with algebra 1 style elimination. That's one way to solve this. We could also solve this with substitution from algebra 1. So if I have a plus b equals 3, negative a plus 7b equals negative 5, then we could solve one of these for the other. For example, I could say, let's take this top equation and solve it for a. So a is equal to 3 minus b, and then substitute that into the second equation. So negative a, which is 3 minus b, plus 7b has to equal negative 5. Negative 3 plus b plus 7b has to be negative 5. So that means 8b has to be negative 2. b is negative 1/4. And then when you back substitute, you get a is 13/4 again. Right? So you can use substitution. You can use elimination. Or if you're on the calculator part of the test, you can use the matrix method, which is to use the coefficients 1, negative 1 for the a's, 1 and 7 for the b's, and augment the matrix with the right-hand side, and then run what's called reduced row echelon form, or RREF on this. You can do that by grabbing a calculator, and then you can go to the matrix menu here. This is 2 rows, 3 columns, so edit matrix A to be 2 rows and 3 columns, and then enter in the coefficients 1, 1, 3. And then negative 1, make sure you use this and not the subtraction key, the negation key. Negative 1, 7, negative 5. And then you can quit back to the command line, go back to the matrix menu, scroll over to the math, and then you should find RREF down here. And then go back into the matrix menu and say to operate on matrix A. I like to go math to fractions. And you can get then that this is after doing reduced row echelon form, RREF, you get the matrix 1, 0, 0, 1, and then this number here is 13/4, and this number is negative 1/4. And so this equation now is 1a plus no b's is 13/4, no a's plus 1b is negative 1/4. So you can use one of these methods to solve. Okay, but now that you have that, that means that this this original integrand here, this is equal to the a, which is 13/4 over x plus 7, plus the b, which is negative 1/4 over x minus 1. So to take the next step in the solution, now that we've done this side work, we can say that the integral is equal to, and I will replace the integrand with this. So it is 13/4 over x plus 7 plus 7, and then plus negative 1/4 over x minus 1. And that allows me to split this into 2 integrals. So we're going to split this into 2 integrals, and I'll move the constant on the outside. So this is 13/4 times the integral of 1 over x plus 7 dx, and then minus 1/4 if I move the negative 1/4 out as a constant over x minus 1 dx. Okay, I'm going to do this integral over here. So now we can do a little u substitution. U would be the entire denominator, x minus 1. The derivative is 1, so du equals dx, and that makes this negative 1/4 integral of 1 over u du. But that makes this negative 1/4 natural log of the u, but the u is the x minus 1. So as long as this is just an x, right, the result of this is just this integral is the natural log of that denominator. And we add c, and we're done. So partial fraction expansion always ends in logarithms, one for each of the linear terms. You want to be careful that if there's a multiplier here, you have to actually do the u substitution to get the constants properly worked out. But that is the idea. Right, so that right there is about the level of difficulty for most. You can choose just one of these methods, whichever one you prefer. Either of these you can do by hand on a no calculator part. This would require a calculator. Sometimes it's just fastest to do it by hand anyway. Okay, here's another one. You can go ahead and try this. Pause the video, factor, do the partial fraction expansion, and then do the integration of the result, and then unpause and see if you got this correct. So what I would do is on the side, I would show some work here that shows how this is factored. So I'm thinking this is x minus 2, x minus 3. And that means that we could do a partial fraction expansion. So I've got this, this is 1 over x minus 2 times x minus 3, which we're going to postulate is equal to some unknown a over x minus 2 plus some different unknown b over x minus 3. Okay, to get a common denominator, what I'm going to do is I'm going to do less writing here. I know this one has to be multiplied by the other one's denominator, each one, right? So I'm just doing that. Okay. And I'm just going to say this is ax minus 3 plus b times x minus 2. Each one's multiplied by the other one's denominator to get a common denominator. And the numerator is 1, right? So at this point, when you've done the common denominators, all the denominators are gone. Okay, multiplying that out, we have ax minus 3a plus bx minus 2b equals 1. So we have a plus b x's, that's these terms. And then the other terms we can combine together into a constant, negative 3a minus 2b. We're going to have to match up the x's. There's currently no x's, so I'm going to just say there are 0 x's plus a constant, which is a 1. And that means that, sorry, the number of x's have to match the number of x's, so a plus b must equal 0. And the number of constants on the left has to equal the constant on the right. Okay, I'm just going to do this by hand. I could get this to cancel really easily if I just multiplied the top by, let's just make it multiply by 3. So 3a plus 3b equals 0, and we have negative 3a minus 2b equals 1. If we add them, those cancel, we get a total of b equals 1. And then a plus that b of 1 has to equal 0, so a is negative 1. So that means that the original system, this is equal to this, and that is equal to the a constant over x minus 2, plus the b constant of 1 over x minus 3, which means I can say this integral is equal to a negative 1 times 1 over x minus 2. This is how much writing I would normally do, and then a positive 1 times 1 over x minus 3. Then you could show the u substitution if you want, but you're not required to. The antiderivative is negative natural log of x minus 2 plus natural log of x minus 3 plus the constant, and then we're done. Okay, so hopefully if you tried that on your own, you got that one right. Okay, so this will work when you have an integrand that has a quadratic in the bottom, or any polynomial that can be factored, and you can factor it. If you're unable to factor it like this, let's say you have x squared plus 2x plus 7, that does not factor, then you have to do the completing the square procedure. Let me just remind you how that would be done. In fact, let's just do this just for comparison. If I tried to factor and I was unable to, I would go through the completing the square procedure, move the 7 off to the side, take this x, we're going to make this a perfect trinomial, so we're missing something here. Take that positive 2 and cut it in half to get a positive 1, square that number and put it here, but because I added a 1, I have to subtract a 1 to balance, so I have plus 6 here. Then you would rewrite the function like this, right? This gets replaced with a single thing like this. But then if you think of this as x plus 1 squared and this as the square root of 6 being squared, you can do this substitution. X plus 1 is u, so then that means the du is dx, and this can be written as a, so that I can write this as 1 over u squared plus a squared du, which means that we've memorized that that's the augmented form of the arctangent shortcut, which is 1 over a arctangent u over a. So it's 1 over square root of 6 arctan of x plus 1 over square root of 6 plus c. Right, so when it's not factorable, we complete the square. If it is factorable, we do partial fractions. The denominator, that. Okay, what if the numerator degree is higher than the denominator degree? So, like in this case where we have an x cubed out here and x squared, first we're going to go ahead and do polynomial division to simplify this. So if I divide this into that, we can use this procedure here. X squared plus x minus 2 divides into x cubed. Now there's a missing x squared term, so I'm going to put 0x squared minus x plus 3. And then the way you do this is you say, what would multiply this x squared to produce an x cubed? That would be an x. So in the x column, I'll put an x. We'll multiply everything here and write the result. So that's going to give me x cubed plus x squared minus 2x. And then we'll subtract that from the thing above it. These we made to cancel. 0 minus x squared is negative x squared. And then this is negative 1 and positive 2, so that is positive 1x. And then I can bring down the 3 here. And then ask the same question, what would I multiply this x squared by to produce a negative x squared? That would be a negative 1. So we'll multiply this by a negative 1, and I get negative x squared minus x plus 2, and we'll subtract the result. These cancel. X minus negative x is, that's going to be 2x, right? Yeah. And then 3 minus 2 is 1, so plus 1. So that means that this divided by this, we're going to replace that with the result. It divided and gave me x minus 1 plus a remainder. This is a remainder, so we write that remainder 2x plus 1 over the divisor x squared plus x minus 2. So you just do this division problem. It produces a result and potentially a remainder. So now I can split this integral. I can say I've got the integral of x dx minus an integral of 1 dx plus an integral of 2x plus 1 over x squared plus x minus 2. Now for this integral, we're going to have to use our partial fraction of the expansion if this factors. So let me switch colors here and let's work with that. Does x squared plus x minus 2 factor? I think it is x. Let's see, what does that turn out to be? Plus 2 minus 1? Yeah, plus 2 minus 1. So that means I could rewrite this as 2x plus 1 over x plus 2 times x minus 1. That's the same integral. And then to handle this, we can say that this 2x plus 1 over that x plus 2x minus 1 equal to an unknown a over x plus 2 plus an unknown b over x minus 1. Okay, so now we'll go through the procedure. We're going to multiply this one by this one's derivative denominator and this one by the opposite denominator. So the a is going to get multiplied by the x minus 2 denominator. The b is going to be multiplied by the x plus 2 denominator so that everything's over the same thing, and that's equal to the current denominator. So that is ax minus a plus bx plus 2b equals 2x plus 1. If we gather like terms, it's a plus bx's plus a constant that's negative a plus 2b equals 2x's plus a constant that's 1, which means the a plus b number of x's has to match the 2x's, and the negative a plus 2b has to match the constant 1. If I solve this system by elimination, if we add these, we get 3b equals 3. So that means b is 1. And if a plus that 1 has to equal 2, a has to be 1. So in this case, these are both 1. So this is equal to 1 over x plus 2 plus 1 over x minus 1, which means I can rewrite this now as an integral 1 over x plus 2 and a separate integral 1 over x minus 1. And now we can do all the integrals. So this integral here is 1/2 x squared. This integral is minus just 1 times the x. This one is the natural log of the x plus 2. And this one is the natural log of x minus 1 plus the c. And we're done. A little bit more complicated. If you have a higher degree polynomial on the top, you can do polynomial division first to split some of it out of that. You'll still have a remainder over that typically, in that part you can do partial fraction expansion for. Okay. Now this can be used for very complicated integrals, although we typically stick to kind of this level over here, this type of level. But let's just talk about what you would do to set this up if we have something like this. So we have a linear factor that's cubed. So in order to set this up, you would have to put a constant over just x minus 5, plus another constant over x minus 5 squared. And then since it's cubed, plus another constant over x minus 5 cubed. Right? And then for this quadratic, you would have to add the equation of a line, dx plus e, over 1 copy of that because it's squared. And then because it's squared, you would have another fx plus g over the x squared plus x plus 1 squared. And then you would get all big common denominator, which means that this, for example, I'm not going to do this, but what you would need to do is you need to multiply by 2 more of these and also 2 of these. Right? This one out here would have to be multiplied by an x minus 5 cubed. This one would need to multiply by an x minus 5 squared plus the other x squared plus x plus 1. You can see how this could get out of hand big time, right? Plus we have 1, 2, 3, 4, 5, 6, 7, which means we're going to have a system of 7 equations in the end. We're going to match up like x to the 7th powers, x to the 6th powers, x to the 5th powers, and so on, and along with the constants. So we won't do anything that complicated, but you can know that you can have any number of multiplicity of linear or quadratic factors in this procedure group order. All right. I have some additional examples here, but they're all just more of the same thing. So I'm going to split this off into a separate interval or a separate video to show additional practice if you want more practice. But I think at this point you've seen everything you need to know. So you can just proceed with this one.